All right, ladies and gentlemen, this is the electrostatics calculation test portion review. This is coming from the additional exercises that you received in class. I'm only going to be doing a portion of those problems. I won't be doing all of them, so just be aware of that. Um, but the ones that I do, I will tell you how they apply to actually um, the other problems as well. I will remind you that your test is Friday, January 28th, or Monday, January 31st, depending on whether you have the A day or B day. You're already online. Go ahead and get the BOPS 4.1 while you're online and make some effort on two of those four problems. And also, my suggestion would be to read over your notes and your statics worksheet number 1 and 2 that we did in class. That'll help you prepare for your multiple choice and fill in the blank sections. All right, so let's get started. We're going to go ahead and start with problem number 1. Problem number 1 and 2 are the same type of problem. So I'm going to do number 1, but it is the same as number 2. Okay, so these are identical type problems. A raindrop acquires a negative charge of, and we know that charge has the variable Q, of 3 times 10 to the negative 18th coulombs as it falls. What is the force? So we're solving for force of attraction when the raindrop is 6 centimeters from the bulb. So that's a distance, but it's in centimeters. So we're going to need to divide by 100 centimeters and convert it into meters, which would be 0.06 meters. And the bulb also has a charge of, so we're going to say this is Q1 and Q2, okay, because this is of my raindrop and this is of my antenna, okay, of 2 times 10 to the negative 6 coulombs. All right. Well, in our notes, we were told that the formula for force is K Q1 Q2 divided by D squared. Well, K is a constant. It's the electrostatics constant that you guys were given. And this is a number that I do believe is on your formula charts. Let me double check that. Yes, it's actually on your physics EOC assessment reference materials under constants and conversions. It is listed as Coulomb's constant. In on that page, it's actually listed as 8.99 times 10 to the ninth. I'm going to make the math even easier, and I'm going to have you use 9 times 10 to the ninth. Okay, and this is Newton meters squared over coulombs squared. Okay, that's the units for that. So we're going to go ahead and substitute in. When we substitute our numbers in, we are going to find that we have 9 times 10 to the ninth Newton meters squared over coulombs squared times 3 times 10 to the negative 18th coulombs times 2 times 10 to the negative 6th coulombs divided by, so the coulombs squared gets canceled out, by 0.06. Oops, let me write my meters there. Oops, that's the end of the day, ladies and gentlemen. That's when I'm recording this. And we have to square this. So that allows us to actually cancel out that. We still keep the number itself squared though. Okay. So when you type this into the calculator, you need to remember to use your EE button for your powers on your times 10. And you should come out with an answer of force that is 1.5 times 10 to the negative 11th. The units are the only units that are left, which is a Newton. And that's your answer to number 1. Realize that number 2 is done exactly the same way. Continuing on. Number 3. Okay, is what I'm going to do next. Number 3 is also the same as number 4. Okay, but we're actually going to do number 3. That's the one I'm going to do. So, number 3 talks about Rocco, the auto body painter. Applies paint to automobiles by electrically charging the car's outer surface and oppositely charging the paint particles that he sprays onto the car. This causes the paint to adhere tightly to the car's surface. If two paint particles of equal charge experience a force of, so we're given a force of 4 times 10 to the negative 8th newtons, and a separation of, so that's our distance, of 0.02 centimeters, what is the charge of each? So we're looking for Q. But you need to realize that this Q is going to be for 1 and 2. All right. Now our distance is in centimeters. We need to divide by 100 centimeters and go ahead and convert it into meters, which makes this a teeny little number. So I'm going to use in scientific notation, which is 2 times 10 to the negative 4 meters. So again, my formula is force equals K Q1 Q2 over D squared. But the thing to realize is this Q1 and this Q2 are supposed to be the same. If that's the case, we can simplify this formula to be F KQ squared over D squared and just solve for Q. Now, also, you do need to remember that you do have K, and we use it as 9 times 10 to the ninth Newton meters squared over coulombs squared. All right, to solve this equation, you need to cross multiply. So we're going to have force times distance equals KQ squared. We need to isolate our variables, so divide by K. Whatever you do to one side, you do to the other. Now you have Q squared, so to get rid of the squared, you'd have to take the square root, and you'll have to do that on both sides. So Q will equal the square root of FD over K. Now remember, you can plug in numbers first and do that if you would like. But when we plug in our numbers now, I'll just have to do 4 times 10 to the negative 8th newtons multiplied by my distance, which is 2 times 10 to the negative 4th meters, divided by my 9 times 10 to the ninth Newton meters squared over coulombs squared. Okay. This is actually going to, we'll be able to cancel out our newtons. We'll be able to cancel out our meters, and then we'll be able to just have that. Then we're going to take our square root, and when we take our square root, we should get 4.22 times 10 to the negative 13th, and now our answer is coulombs. Okay, because we're looking for charge. Don't forget, oh, I know what I didn't show you. Okay, I lost my squared on my D, ladies and gentlemen. So you need to make sure that you don't do that same mistake that I just made, which was that I lost this lovely little squared from right here. I forgot to carry it with me everywhere. So that's why my meters canceled out. I was like, why is that not working? But that's why the meters squared was able to be canceled out. So you will have to take 2 times 10 to the negative 4 squared times 4 times 10 to the negative 8, and then divide it by 9 times 10 to the ninth. That'll, after you take the square root of all of that, then you will get 4.22 times 10 to the negative 13th. Sorry about that. Moving on. The next problem that I'm going to do is number 5. There is not another problem like number 5 on your assignment. That's why I wanted to do number 5. Probably hear all my papers rustling around. Number 5 is about Whiz the Cat. And Whiz the Cat is batting ping pong balls. Each ball is going to acquire a positive charge, so that's Q1 and Q2. 2 are both going to be 3.5 times 10 to the negative ninth coulombs. I know that there's a force acting on them of 6.0 times 10 to the negative fifth newtons, and I want to know how far apart they are. Okay, so I also have K because that's going to be 9 times 10 to the ninth Newton meters squared over Coulomb squared. So my formula is still F equals K Q, it's going to be squared over D squared. Don't forget the squared. But this time I need to solve for the D that's here on the bottom. If that's the case, then I'm actually going to have to cross multiply first, which will give me FD squared equals KQ squared. I'll have to divide by F to isolate my variable. I'll now have D squared equals KQ squared divided by F. And to get D squared by itself, I'll have to take the square root of both sides. This is very similar to number 3 and 4, except again, I'm looking for my denominator instead of one of my numerators. So now I'm going to plug in what I know. K is 9 times 10 to the ninth, and that was Newton meters squared over coulombs squared. I'm going to multiply that by 3.5 times 10 to the negative ninth coulombs squared. So that's going to allow me to cancel out this coulomb squared. And then I'm going to divide by my force, which is 6 times 10 to the negative fifth newtons. Newtons will cancel out. When you take the square root of your meters, your answer will be in meters. So you'll multiply 9 EE to the 9 EE9 times 3.5 EE negative 9 squared, because we need to make sure we don't lose the squared, even though I canceled it out over here with my unit, divided by 6 EE negative 5 equals, then hit the square root button. Always make sure you hit the equals button after you do your inner calculation before you hit the square root. Otherwise, the calculator won't work for you properly. So when you get done doing that calculation, you should get an answer of 0.04 meters that they were apart, or 4.29 times 10 to the negative 2 meters. And then it asks, was there a force of attraction or repulsion between the two balls? Well, you will remember that we had two balls. They both are a positive charge because we had two ping pong balls that the cat was playing with. If they both have a positive charge, the basic rule of electrostatics says that like charges repel and unlike charges attract. So that would mean that this was repulsion because they are like charges. Moving on. All right, the next one I'm going to do is number 7. Number 6 and number 7 are very similar to each other, but I'm going to do number 7. All right. Number 7 talks about the human body and the nerve cells working in it. And we're told that we have a charge on the sodium ion of 1.6 times 10 to the negative 19th coulombs. We're told that the electric force being applied is 2 times 10 to the negative 12 newtons, and we're asked what the electric field is. Well, we were given the equation in the notes, or you were, that it was force divided by um, charge. Okay, well, force is 2 times 10 to the negative 12 newtons divided by 1.6 times 10 to the negative 19th coulombs when you do the work. So your E ends up becoming 1.25 times 10 to the 7th power. Now these units don't cancel out in any way, so they stay exactly as they appear, newtons per coulomb. And that's your answer. Again, number 6 and 7 are very similar to each other. The next one I'm doing is number 8. Number 8 isn't really like any of them that are on the rest of the paper, but you do need to be aware that you could see problems like this on the test. We have two Van de Graaff generators, which I'm just going to do the actual spheres of the Van de Graaff generators because remember, we've dealt with these in class and they kind of look like that. All right. But they are separated by a distance of their centers of 0.5 meters, we're told. Okay. Now we are also told that one of them is going to be charged with, and I'm going to go ahead and make the left-hand one, 3 times 10 to the negative 2 coulombs, and we're told it's positive. And then this other one is 2 times 10 to the negative 2 coulombs, but it's negative. You'll remember electric force lines say that positives go out or away, the electric field does, and negatives go in. Okay, so the thought process is think about dropping a positive particle next to it. If you drop a positive particle next to it, is the electric field going to pull it in or push it out? Well, on the pink one here, if I drop a positive particle next to it, it's going to pull it in. So that's why I draw those arrows inwards. And if I drop a positive particle next to the green one over here, it's going to push it out. All right, because they're going to repel each other. We want to know what the actual electric force is, or electric field, excuse me, magnitude and direction halfway between. Well, halfway between is right there. So that makes my distance now instead of 0.5, 0.25 meters. Well, I have an electric field over here, and I have an electric field over here. To find electric field, it is kq over d squared. And this one will be kq over d squared as well. Now the thing to look at is right here. Notice we're talking about in the middle. Both of those arrows are pointing in the same direction. If we consider those vectors, if vectors are pointing in the same direction, what do we do to them? Hopefully you said we add them, Miss C. Okay, so once you find this electric field and this electric field, you are going to add them together because they're both pointing in the same direction. So I'll find my green electric field by doing 9 times 10 to the ninth multiplied by 3 times 10 to the negative 2 over my distance, which is 0.25 squared. I'm going to add that to my 9 times 10 to the ninth multiplied by 2 times 10 to the negative 2 divided by my 0.25 squared. Now remember, you don't use this negative that's on the pink right here down here in the problem because it's just used to help you figure out which direction the vectors are going. The sign is used to help figure out direction. So when we do these together and we figure out our math, you should end up with an answer of 7.2 times 10 to the ninth. This is newtons per coulomb, the electric field is. So if that's the case, we're going to go ahead and say this is our magnitude. But they also wanted to know a direction. Go back up to your green highlight. Okay, the direction is which way, left or right? Well, ladies and gentlemen, it is to the right here. Or you could say towards Q2 or towards the negative. Either one, all of those are the same thing. All right, moving on. I am now on number 10. Number 10 really isn't like any of the others either. On number 10, it talks about the Milliken Oil Drop experiment, and we are told that that the electric force is equal to the gravitational force. All right. and it's acting on a mass. So again, I'm doing number 10. Sorry, let me write this down. And we're told that the mass of the drop is 1.1 times 10 to the negative 14th kilograms. We want to know what is the charge, so we want to know Q on the drop if it remains stationary in an electric field that is 1.72 times 10 to the fifth newtons per coulomb. Well, I'm going to remind you that you can figure out a force. If you know, if you remember, force equals mass times gravity. Well, we have the mass of 1.1 times 10 to the negative 14th kilograms. We know gravity to be 10, okay, and that's meters per second squared. So you're able to find a force that is 1.1 times 10 to the negative 13th newtons. Well, there's a formula that says E equals force divided by Q. So we could rearrange that to actually say Q equals F divided by E. If that's the case, then we're just doing 1.1 times 10 to the negative 13th newtons divided by our electric field of 1.72 times 10 to the fifth newtons per coulomb. The newtons cancels out, and you end up with an answer of 6.4 times 10 to the negative 19th coulombs. Now that's just the first answer though. The first question said, what is the charge? There we go. We've got charge. Then it says, how many extra electrons are there on this particular oil drop? Well, if you remember in your notes, I told you that for every 1 coulomb, it was 6.25 times 10 to the 18th electrons. All right? If we know this is 6.4 times 10 to the negative 19th coulombs, then we can say for every 1 coulomb, remember, there's 6.25 times 10 to the 18th electrons. Cancel out your coulombs, do your math, and you'll find out that there are 4 extra electrons here. So remember, this little number right here came in handy from your notes. You might need it. So continuing on. I'm going to skip to do number 11. Number 11 talks about 18th century Europe. La, 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 la. You have the paper in front of you. It's got 133-year period, 400 church steeples, blah, blah, blah. A lightning bolt discharges a charge. So here's information we want to talk about. 30 coulombs from a cloud, a steeple, across a potential difference. Well, potential difference is a voltage. And so potential difference is 15,000 volts. They want to know how much energy is lost by the cloud and gained by the steeple. So they roughly want to know how much work was done. Sorry about that. So there's a formula that says V equals W over Q. Okay, because it is potential difference equals work over test charge. If that's the case, you're going to cross multiply. So you're going to say 30 coulombs times 15,000 volts gives you the work that you're solving for. And that should be 450,000. And work has the units of joules. Remember, work and energy are the same type of thing. And finally, I'm going to do number 12. Number 12 and 13 are very similar, but I'm doing number 12. Okay. Number 12, we go back to exercise 7, which we already did, about the potential difference, or about the sodium in the nerve cell. All right. Now we're going to say that we have a potential difference of 0.089. Okay. Realize that between the inside and the outside, if it is a potential difference, then this is a voltage. They don't have units on that number, which I don't understand why, but it should be voltage, yes. Um, and then we should be able to go back and look at that problem and realize that our E is going to be 1.25 times 10 to the 7th newtons per coulomb. That was our electric field that we calculated on that problem. Well, we want to know how far. Is that what we want to know? How thick. So we're looking for distance. Okay. Well, there's a formula that says originally that electric field equals the potential difference divided by the change in distance or the separation between plates, things like that. Okay, so we're going to do the separation between the inside and the outside of the cell. So if that's the case, we know 1.25 times 10 to the 7th newtons per coulomb equals our 0.089 volts over our change in distance or how thick it is. Okay, when you do your math, you're going to have to cross multiply or just switch positions. So we have delta D equals our 0.089 divided by 1.25, oops, times 10 to the 7th. And you end up with an answer of 7.12 times 10 to the negative ninth meters. All right, so that should be that. That gives you all the problems that I was really holding you responsible for. And good luck on your test. Remember, if you need me, come see me and I can further explain some of this stuff. But hopefully, at least by doing a large portion of these, you've had a chance to see how they're done. Good luck. Check you later.